Thanks for listening in today. I'm Ashwin and I'm with Kevin, Tony, and Nielsen, and we're here to present our solution, GeoSense. For our project, we decided to focus our tracker on the southern royal albatross. So before we get into the device, let's talk a little bit about why we even need it in the first place. This particular species was classified as endangered, but has recently been reclassified as vulnerable. And then there's a few causes to this status. One would be fishing, which does sound very unusual, but many net-based fisheries unintentionally end up trapping the birds as well. This leads us to our second cause, injury from human traps. They tend to scavenge on baited longline hooks or collide with trawler cables, which cause injury and sometimes most of the time death even. And lastly, perhaps the biggest cause is the changing climates caused by global warmings. This is changing the behavior of the migrating birds, and we need to keep up with these changes. So research has been done, like dozens of studies and on thousands of birds, to conserve the areas where the birds frequently visit. This is possible because they're highly philopatric, which means that every year to breed, they return to the same place. So as we do more research, we can do our best to conserve these places to preserve the species. However, we're still learning about them. The more we research them, the more new patterns we discover. So what's the point of GeoSense? We identified 4 major issues with the devices that exist on the market already. One of these is that the devices only collect very specific data, which is usually location data. This is because they mostly use GPS radars, which lead us to our second problem. These devices mostly use GPS radars, and those that use light sensors are quite inaccurate compared to the previous. It's also usually hard either for the researchers to recover the device, since they're like attached to the bird and they'll have to catch the birds one by one and remove the devices, or they could be implants that are permanently inside the birds and can't be recovered, so they're one-time use. However, the biggest problem possibly is data loss. So if we go through all the trouble to collect the data, but it's corrupt at the end, or the bird is lost, that's probably the biggest problem since we lose all the data. Our goal with GeoSense is to address these issues as best we can.
Thank you, Ashwin. For these problems, there are some solutions we have thought of, and these are the ways that what we can do targeting these problems. For example, for solve the data, we could use GPS or telemetry data to provide a higher accuracy towards location. And since the data type is very simple, we can always include a barometer and include a magnetism data or like gesture of the albatross. And for the data type, we thought of using a Bluetooth to sync the different device on the bird so that we can save as much data as possible in case any device were lost in the process. And for solving the power problem, we come up with three solutions, which is solar panels using customizable battery, and also have a backup batteries to increase the lifetime of the device. For other features, we sort of come up with some solutions like using special software, compare different sensors data, like comparing barometer and the light sensor data so that we can get a more accurate geolocation of the bird and some other features. For the explanation of this, we choose using a barometer sensor to record the pressure data, which can provide a higher behavior graph of the bird during different air pressure, during different weather. And we choose to use a Bluetooth unit to sync the data on different devices. And also we use Bluetooth as a release mechanism when the bird is within the range of our device so that we can collect the device more easily. We don't need to chase the bird, and we can use Bluetooth to enable a speaker to make some noise to help scientists locate where the device has been. Also, we have some solar panels attached to the bird to provide a longer lifetime of the device. And from our calculation, the solar panel will provide a higher power compared to the power consumption of the device. So in theory, this device can last indefinitely. And for the justification and technological part, I will hand over to Nelson.
All right. Thanks, Tony. So I'll go through the technical justification of our project. So here we have a block diagram of how our system is built together. Let's look at the power section for right now. So our power section consists of 2 solar panels, as Tony said, and each solar panel has a maximum point tracking converter, so we can get the maximum power from each solar panel. These solar panels will feed into 2 batteries, which are both 400 milliamps, and this will give a 10-volt power supply to a QVGA board, which has regulators from 10 to 5 and 5 from 3.3. The QVGA board also has 4 UART interfaces, 3 I2Cs, 2 PWMs, and 1 ADC. So what does that give us? So with our Bluetooth module, for our Bluetooth sync features, we can use UART and 3.3 source to our QVGA board. And likewise, we can use I2C for a barometer sensor to receive digital data from it. Our light sensor, I'll go on about it in the next slide, but for now, it uses our ADC, and it's not a problem because we only have 1 ADC on the board. And for a Bluetooth release mechanism, what we're trying to implement is a PWM signal from our board to the motor, so that will trigger a spring release mechanism and release the sensor from the bird. So let's look at one of the most important features of our project, the light sensor. So our light sensor is we refined it to a level of accuracy where it's able to detect sunsets and dawns at 400 lux. So we selected a resistance of 4.3 ohms such that it can linearly detect significant changes between 0 to 600 lux. We also tested our light sensor's accuracy by making a light generator device that can vary between 0 to 10,000 lux. And on top of that, we use white light because it covered most wavelengths, so sunlight will cover as well. Now I'll pass on to Kevin. He'll elaborate on further justifications.
All right, thanks, Nielsen. For rest justification part, firstly, we consider about the total weight of the device. Normally, a 1,000 Royal Ultrabus is about 7.5 kilograms. Since we require to control the weight of device below 5% of the bird's weight, which is about 775 grams, so we calculate that the weight of sensors are around 10 grams. For the power part, the 2 batteries weight are around 30 grams. The solar panels are around 20 grams. 2 batteries modules is about 20 grams. The chips and regulators are around 150 grams. The motor is 20 grams, and the rest of the shell is like 20 grams. So total of them is 270 grams, which is about 3.5% and is below 5%. In addition, we calculate the power usage of the device. There are 2 modes of it, which helps us to maximize the last days for it. In the fully active mode, the total current is around 190 milliamps. Since our device records every 10 minutes, and the barometer detects the motion of the bird, if it takes a rest, the sensor won't working, which is idle mode, and the current is around 19 milliamps. So for our 4,800 milliamp times hours battery, we divided by the average current to get the working hour, which is around 1 week. So we use a 1.5 watt solar panel connected to the our system as a primary power supply. Last, for the barometer, the accuracy range is between minus 10 meter and 9,000 meters, and the Bluetooth range is around 50 meters in power saving mode. That's everything about our presentation. Thanks for watching.